All right, let's jump right into this explainer. A huge welcome to all the grade 9 students tuning in from St. Paul American School Clark. Today, we're tackling Geometry Unit 2, Lesson 3, Transformations with Geometry Software. If you're looking to totally level up your understanding of the coordinate plane, you are in the exact right spot. We're going to see how incredibly powerful tools like Desmos and GeoGebra take boring, static shapes and turn them into fully dynamic, programmable objects.
To really set the stage for today, let's think about geometry software exactly how Mr. Watson describes it on GeoGebra. He calls it a magic training unit. I mean, how cool is that perspective? Instead of just sketching on graph paper with a tired pencil and ruler, you're essentially learning how to cast mathematical spells. The software commands you learn act just like spells, like Verdo figure, giving you the power to manipulate and analyze geometry in real time. It completely changes how we interact with math.
Section 1. Explaining software functions. Math as programmable rules.
When we jump into software, we kind of have to rethink our basic definitions. We literally have to define a transformation strictly as a function. Think about it like algebra. In algebra, an equation takes an x input and spits out a y output, right? Well, a geometric transformation takes an entire point, or even a whole set of points that make up a shape on the plane, as its input. The software processes that input through a specific rule, and then boom, it outputs new points to create your transformed image. You're defining a domain and a range, but you're doing it entirely with visual coordinates.
And this perfectly illustrates how we actually execute those functions. In software like Desmos, you've got this super handy expression list right on the side of your screen. You can literally grab an object, like a point, and drag it directly into that expression list to reveal its exact coordinates. From there, you use that list to type out specific algebraic commands. It's literally where geometry meets algebra.
Section 2. Worked example. Rotating objects. Casting a rotation spell.
Okay, so the absolute most crucial thing here is following this exact sequence in the Desmos geometry tool. First up, you use the Select tool to grab your pre-image. Let's just say it's a triangle you built. Second, pop open the Transform and Construct menu from the toolbar and pick Rotate. Third, you'll follow the little on-screen prompt to choose a point that's going to act as your center of rotation. And finally, step 4, you just punch in the angle you want to rotate by. Could be 90 degrees, 180 degrees, clockwise, counterclockwise, you name it.
But wait, here's where the magic actually happens. If you swap out a static angle number in that input box for a variable letter, let's just use the letter A, and hit Go, the software automatically generates a slider right there in your expression list. By just dragging that slider back and forth, you instantly visualize countless dynamic rotations of your pre-image. You're not just drawing one static rotated triangle anymore. You're actively animating its entire rotational path across the coordinate plane.
Section 3. Misconception check. Preserving distance. Do all transformations keep shapes identical? So we really need to divide our transformations into two distinct categories, rigid and non-rigid. Let's compare our rotation, which is a rigid transformation, to the others. When you rotate a triangle, it perfectly preserves both the distance between its points and the exact measure of its inside angles. It's the exact same shape, just spun around. On the flip side, non-rigid transformations, like dilations or horizontal stretches, fundamentally alter those distances. A dilation scales the object up or down from a center point using a scale factor, which completely changes the side length. Let's take a closer look at a very specific non-rigid transformation, using a great example straight from illustrative mathematics. Imagine you have a rule that maps every coordinate xy to a brand new coordinate 3xy. This is what we call a horizontal stretch, because you're applying a scale factor of 3 to the x-axis, but leaving the y-axis entirely alone, you visibly distort the shape. If you were to use the Pythagorean theorem to check your new side lengths, you'd quickly find they don't match the original at all. Since the scale factor is different on the two axes, the new shape isn't just a different size, it's not even similar to the original. Distances and angles are totally broken here. They are absolutely no longer preserved.
Section 4. Formative check. Software commands. Test your programming skills.
All right, think about the inputs and the strict syntax required by the software to command this specific transformation. If you wanted to apply a 90-degree counterclockwise rotation around the origin point 0, 0 to any given object x, what exactly would you type into the Desmos expression list? Take a quick second to think about all the pieces you need: the name of the function, the object itself, the center, and of course, the angle.
And here is the exact correct syntax. You define it as a function. Capital R of x equals rotate, open parentheses, x, comma, the coordinate point 0, 0, 90, close parentheses. In this command, x isn't just some random number, it represents whatever geometry object you decide to click on later. You have essentially just written a reusable computer program for a geometric rotation. How awesome is that?
Section 5. Recap. Software transformations. Your new dynamic toolkit.
Let's lock in the core takeaways from today's explainer. First, geometry software forces us to view transformations as precise functions, with clear inputs and outputs. Second, tools like Desmos let you execute rotations and dilations dynamically using specific menus or expression lists. Third, by subbing in variables instead of static numbers, you can create sliders that animate your transformations in real time. And finally, always remember the huge difference in preservation. Rigid transformations, like rotations, perfectly preserve a shape's distances and angles, while non-rigid transformations, like horizontal stretches and dilations, change those distances entirely.
I'm going to leave you with this final thought to ponder. If geometry software transforms static, paper-based math into this incredible playground of programmable functions, what complex, real-world movements, like maybe the intricate gears of an engine or the precise orbit of a satellite, could you model next with just a few simple equations? The possibilities with dynamic geometry are literally endless. Thanks so much for joining me on this explainer, and keep exploring.